Hello, everyone. My name is Nick Piskrich, and I'm a first-year doctoral student at the University of Central Florida. I am working under Dr. Carrie Donaldson-Hanna, and today I will discuss my investigation of the compositional characterization of the four largest irregular Mare patches, also known as IMPs, via Moon Mineralogy Mapper data analysis. This image here shows that IMPs are unusual. They have two very different morphologies, a hummocky, blocky terrain at lower elevations and a smooth, block-free terrain at high elevations. IMPs also have anomalously young ages, as young as 10 million years old based on crater model ages. And in our study, we seek to understand if IMPs are similar in composition and mineralogy in comparison to their surrounding terrains. So first, I will give an introduction of irregular Mare patches, some background about basaltic volcanism and the distribution of IMPs, and then I will touch on the motivation for this analysis, followed by the prior investigations of IMPs, their proposed formation mechanisms, and finally, I will discuss our preliminary results and future work plan. So IMPs are hypothesized lunar volcanic features that are relatively small, the smallest being about 15 meters and the largest being around 5,000 meters in maximum length. As mentioned before, they show two different morphologic deposits. They can also be found in a wide variety of geologic contexts. The four IMPs that we plan to study in this analysis are the four largest ones in spatial extent, and those are Sosogenes, Ina, Cauchy 5, and Mascaline. These are shown here in the narrow angle camera images from the Lunar Reconnaissance Orbiter on the right. And to date, we have analyzed and characterized the general compositional diversity of both Ina and Sosogenes. IMPs are distributed throughout the lunar near side. The current documented number of IMPs is 91 after a recent catalog in 2020. The image on the right here shows the spatial distribution of IMPs overlain on a LOLA topographic base map. IMPs are primarily located in host Mare regions, but they can occur in a wide variety of geologic contexts. It is estimated that the flood basaltic emplacement of Mare regions occurred between 4 and 3 billion years ago, with a peak around 3.5 billion years ago. However, the lack of superposed craters on the morphologically smooth deposits of IMPs indicate that they may be relatively young, possibly as young as 10 million years old. So our motivation for this analysis involves understanding lunar thermal interior evolution. Compositional characterization and understanding IMP formation mechanisms can indicate to us the duration of lunar volcanism and when volcanism may have turned off on the moon. This information could be utilized in numerical simulations of modeling the lunar interior. And finally, IMPs represent ideal sites for commercial landers, rovers, and sample return missions. So the diagram here on the right shows how complex lunar volcanic history really is. I have highlighted the range of geologic timescales on this figure at the bottom. Time before present is shown on the x-axis in billions of years before present. And this figure really gives you an idea of how young the IMP model ages are in comparison to the origin of the moon and the solidification of the lunar magma ocean. So there is a large gap between the Mare basalt source region formation and even the youngest surface Mare deposit that's been dated, and that gap is around 3 billion years. But the IMP model ages are all the way in the Copernican geologic period, less than 100 million years old. So if these model ages are correct, this could fundamentally change the way that we think about lunar volcanic history. So numerous investigations and analyses have been performed for IMPs with a wide variety of data sets in order to understand many of their different characteristics. So I've highlighted the top approach here, which is our approach looking at the compositional characterization, and we're using visible and near infrared and thermal infrared spectroscopy with the Moon Mineralogy Mapper and Diviner Lunar Radiometer data sets. So our compositional analysis is unique in that it can be linked with other studies involving geologic settings and contexts, morphologies, numerical simulations, and compared with terrestrial field studies of lava flows, all in order to gain a better understanding and to better constrain IMP formation mechanisms, and IMP origin scenarios. So many outstanding questions about IMPs are unknown, particularly their origins and formation mechanisms. So our analysis attempts to answer one of these major unknowns. Are the compositions and mineralogies of IMP interiors similar to those of their host Mare and the surrounding materials? And if so, what implications does this have for IMP formation mechanisms and origins, and ultimately lunar volcanic history as a whole? So a variety of formation mechanisms and origin scenarios for IMPs have been proposed since 1972. Schultz et al. In 2006 hypothesized that IMPs could result from caldera collapse at a summit, with the mounds being formed later via lava extrusions. Gary et al. In 2012 suggested that the smooth mounds would have inflated, and breakouts of these margins became sources of surface flows that would have created the hummocky and blocky units. Carter et al. In 2013 suggested that IMP-like terrains are surrounded by fine-grained, block-free material that is consistent with pyroclastic deposits, or these explosive eruption deposits. Braden et al. In 2014 suggested that the smooth mounds of IMPs could represent small magma extrusions, while the rough floor units are disrupted lava pond crusts. And finally, Kiao et al. In 2017 suggests that the hummocky or blocky units could represent a solidified lava lake crust, while the mounds could represent solidified magma foam. So in our analysis, we used M-cubed level 2 reflectance data that was ground truth corrected based on the time of observation. The M-cube data for these optical periods was taken in global mode, which contains 85 wavelength channels between 430 and 3000 nanometers. The figure here on the left shows a 3D image cube from the Moon Mineralogy Mapper, and each of the image cubes or strips that we have contain 2 spatial dimensions and 1 spectral dimension. So as seen in the figures on the right, different rock-forming minerals on the Moon can produce these distinct absorption bands. The typical minerals that are found in lunar igneous rocks are included here, which include pyroxene, olivine, and plagioclase. And their absorption depths, their band centers, and the band widths can all be influenced by a wide variety of factors. We primarily focus here on the 1 and the 2 micron wavelength bands in these visible and near-infrared spectra, because these are the regions that tend to exhibit absorptions in mafic minerals due to the occurrence of iron in the M1 and M2 crystallographic sites. So we extracted planetary data system spectra and implemented a continuum removal approach developed by Moriarty et al. In 2016 in order to quantify the locations of band centers in our spectra, which is one parameter that can be indicative of composition. So for INA, we chose regions in the IMP interior and the surrounding terrains via principal component band analyses and the utilization of high-resolution narrow-angle camera images from the Lunar Reconnaissance Orbiter in order to distinguish the smooth mounds from the blocky terrain. The reconnaissance of the 4 major IMPs revealed that the dominant spectroscopic signature indicated pyroxene-like compositions, so our continuum removal approach was implemented for spectra that were similar to pyroxenes. The colors for each of the subgroups represented here are shown at the top left. Red for the smooth mounds, blue for the hummocky terrain, green is an average over the entire IMP interior, pink is the regolith, orange is the dark halos, which are compositionally distinct deposits that tend to be darker in albedo surrounding some of the IMPs. And finally, brown is the fresh craters. The relative size of the squares indicate the pixel averages that were taken for each of the extracted spectra. So all of these spectra are either 2x2, 3x3, or 5x5 pixel averages. So an arithmetic average was computed for all of the spectra within each subgroup. The figures on the right here show the spectra of both PDS and continuum removed for each of the regions on the M-cubed band at the left. We find that for INA, the interior is relatively distinct from the surroundings. Ina's interior also seems to exhibit stronger absorption bands at both the 1 and 2 micron wavelengths when compared to the surrounding regions. The average region of the Ina interior at about 250 pixels seems to be an averaging of both the smooth mounds and the hummocky terrain. And Ina seems to be the most distinct from the surrounding regolith, the dark halo features, and the fresh craters. And I have drawn fixed lines here at 1 and 2 microns in order to show you the subtle differences between the band center locations for each of these subgroups. So a similar analysis was performed for Sosogenes. We extracted spectra again from the smooth mounds, the hummocky terrain, the regolith, the dark, more mature craters this time, and the fresh, immature craters, and finally the average interior of the Sosogenes imp as a whole. So reconnaissance of this region again revealed that the compositions were initially indicative of pyroxene due to noticeable absorptions near the 1 and 2 micron bands. So for our results, we find that the spectra for Sosogenes in general are highly similar to the surrounding terrains. This is different from the trend observed for Ina, which was dissimilar to its surrounding regions. This could suggest that their formation mechanisms may be different. In both Ina and Sosogenes, the average blocky terrain shown in blue appears to exhibit the strongest absorption bands. And again, the entire averaged interior over 200 pixels appears to be somewhere in between the spectral shapes and the spectral signatures for the smooth mounds and the hummocky terrain. The regolith and dark craters appear to have weaker absorption bands, which makes sense because these materials may have been exposed to space weathering. The accumulation of nanophase iron and agglutinates could contribute to the dampening of the spectral absorption bands for these regions. And in particular here, we also see that even the spectra for the fresh craters shown in brown seems to be very similar to the spectrum of Sosogenes interior shown in green. So on the left are the narrow angle camera images that we used to extract spectra, looking at the defined regions of the bright albedo and rough terrain in both of these images, and the dark albedo and smooth mound terrains that we were differentiating between. The spectral shapes of the smooth mounds here are shown for Ina and Sosogenes, and the spectral shapes appear to be similar, and their band 1 and band 2 centers appear to be relatively comparable. Sosogenes appears to have a band 1 center slightly leftward or shortward of Ina's, and Ina's smooth mounds also appear to have a deeper band 1 absorption depth. We did the same thing for the comparison with the hummocky terrains as well. Again, the spectral shapes look relatively similar, and both Ina and Sosogenes have comparable absorption depths at both band 1 and band 2. Instrumental artifacts near 1500 microns in the MQ dataset could cause this strange disparity here seen in the Ina hummocky terrain spectra, but ultimately it could be possible that the difference in hummocky and smooth spectral data here is due to a result of the differences in their geologic context. Ina is located on the floor of a small shield volcano summit pit crater, while Sosogenes is located within a sinuous rill. So using the continuum removal technique applied by Moriarty et al. In 2016, we fit interpolated polynomials to the absorption bands at 1 and 2 microns over a defined wavelength range. The first wavelength range goes from 700 to 1200 nanometers, and the second wavelength range goes from 1575 nanometers to around 2800 nanometers. And this is just an example of a fitted polynomial for the Sosogenes fresh craters. Then we were able to extract the band center locations by finding the minima of these interpolated polynomials. So now they are shown here on the right, the band centers, the approximate band center locations. And observing this parameter space, we can see that Sosogenes and its surrounding terrain have a wider range of band 1 centers when compared to the range of band 1 centers for Ina. The ranges of the band 2 center positions, however, for both Ina and Sosogenese appear relatively similar. We can also see here that Sosogenese, the average interior is very close to that of the band center positions of the fresh craters. And we can also see that Ina's averaged 250 pixel region appears to be very close to the band center positions of both the smooth and the hummocky terrains. And the smooth regions of Sosogenese appear to have similar band centers to the dark craters and the regolith. And finally, the hummocky terrains for both Sosogenese and Ina show very similar band center positions. So our future work will involve obtaining a more precise estimate for these band centers by further interpolating onto finer grids to find more exact wavelength positions of band centers. And data is also available from other optical periods of the M-cubed observations. So we would like to confirm our results with additional data from different optical periods. And we then intend to continue the analysis with the thermal infrared measurements with the Diviner lunar radiometer. And particularly, we're going to use the 3 channels near the 8 micron wavelength region to map the Christensen feature in these silicate minerals. And finally, we would like to describe the major compositional trends based on the geological context and move our analysis to the point where we can look at the rest of the 87 IMPs, or at least those that are capable of being resolved by the M-cubed and Diviner datasets. Thank you very much for your time.